All right, I'm assuming everyone can hear me. Is that correct?
Yes. Yeah,
Thank you, Roshan. Yeah. All right, so for those that are still joining, I'm just going to give a very, very brief introduction so you know what's happening. I've seen some names on the Zoom channel that are new, folks that might have just woken up in their time zone now and joined and weren't here for our earlier smell session. And probably some people on YouTube are also new to the stream. And so I just wanted to give a very, very brief introduction. This is the Smell, Taste, and Temperature Symposium that my PG student Jazz Brooks from the Human-Computer Integration Lab at the University of Chicago is organizing together with myself. We just went through the proceedings of Kai and we selected as many papers as we could, honestly, that were on smell, taste, and temperature, which are three topics that are very dear to us. And we really wanted to get together all these people because, as many of you know, Kai, which is the ACM, Kai, the premier venue for human-computer interaction, was canceled this year due to the COVID pandemic. And we thought, well, we got to get these people in the same Zoom room, virtual room, and kind of talk about these topics at length without time restrictions and all that. And so you're joining us to hear about 11 talks that are from this conference, the Kai 2020, and we structure them in 3 sessions. And you are here now at the temperature session, which is the middle one. And we just heard from the smell session earlier today, about 2 hours ago. And if you can, please, if it's available in your time zone and possible, join us later as well for this session. We moved it to a little bit later, so there's a big break, but that's because we wanted to accommodate the authors in Asia that really are the core of that session too. And so we are now in the temperature session. The earliest smell session was chaired by Emanuela, who did an amazing job, and now we have Roshan from Rochester Institute of Technology chairing this session. If you know his work and if you're in the Kai community, you certainly know his work on temperature. He's a real expert in this topic. And later we have Nimesha Ranasinghe from the University of Maine talking and moderating us through the taste session, the one that happens later. Without further ado, I also wanted to just say the objective is not just to see these talks, which I think is really important because they're fantastic, but also to engage. Feel free to have side discussions on the Zoom channel, contact people directly. A feature to talk to people directly is enabled. If you're on YouTube, reach out to people via email and so forth. You can find their emails also on our page. So really, we want to foster collaboration and discussion and engagement amongst all of you. And I know many of you aren't from the academic community, but we really wanted to have you here as well, artists and practitioners and industry folks that are interested in smell, taste, and temperature. So that's all, and I'm going to pass the baton to Roshan, who's going to lead us into this session on temperature.
Hi, everyone. So welcome to the session on temperature. So thank you very much to Pedro Lopez and also Jazz Brooks for organizing this event. And it's I think, a great opportunity for all of us to come together and discuss these topics. So in the temperature session, we have a few fantastic talks that are covering from actuator design to applications of temperature for different purposes. So without further ado, I'd like to move on to the first talk. And before that, I'd like to mention that there are some, so if you have any questions that you would like to ask the authors, please add them onto the chat in the Zoom session. And at the end of each talk, we'll have a couple of minutes for Q&A. And at the end of the whole session, we'll have some sort of a panel discussion involving all the authors. So yeah, let's move on to the first talk, which is ThermalBitDisplay, a haptic display providing thermal feedback perceived differently depending on body parts. That's presented by Arinobu Niijima. So yeah, Arinobu, please go ahead. Jess, I think we cannot hear the presentation. Sorry about that.
Touch device.
Okay.
I am Arinobu Niijima from NTT Corporation. We will present ThermalBitDisplay, which is a haptic display provides different thermal feedback perceived differently depending on body parts. ThermalBitDisplay consists of tiny patch device in the battery. It provides weak thermal stimulation. The thermal feedback is different depending on how to touch the device. When weak thermal stimulation, such as changing 2 degrees Celsius, is presented, the user does not feel it as being warm on the finger, but does perceive it as being warm on the lips. There are some studies using press devices embedded in wearable devices to apply thermal feedback to several parts of the body, such as wrists and fingers. Our motivation is to explore new interaction using thermal feedback for new applications that are different from those using vibro-tactile feedback. Our method is based on physiological and psychophysical studies on thermal perception. One is the different thresholds of thermal sensitivity for each body part. The lips are the most sensitive part of the body, and the extremities are insensitive. Therefore, weak thermal stimulation can be perceived on the lips. Another important feature is spatial summation of thermal perception. Due to it, the area of stimulation plays a prominent role in the thermal threshold. For example, if the area of foam stimulation doubles, the threshold can be halved. In other words, the smaller the area is, the more difficult to be perceived. Based on that, we decided to use the smallest press devices to make the differences in the detection thresholds to thermal stimulation between each body part larger. We have conducted a preliminary test to investigate different detection thresholds by an adjustment method with a tiny press device. The results were consistent with previous studies. The more sensitive the body part was, the lower the detection threshold for warming and cooling. Then we have conducted an experiment with 12 participants. The question is that the thermal feedback can be perceived differently between different sensitive body parts. The task is to discriminate two different thermal stimuli presented on the finger, the wrist, and the lips. One stimulation is 25 degrees Celsius and the other is 27 degrees Celsius presented by the tiny press device. Participants conducted the task 20 times for each body part. The results showed that the median accuracy was 55%, 65%, and 95% respectively. These results mean that the participants could perceive the on stimulation only on the lips. Therefore, the thermal feedback is perceived differently between on the finger and the lips. Next, we present ThermalBitDisplay with 3 press devices. The outer press devices were cold and the center one was hot. When touching them with a finger, the user perceives cold and no pain due to spatial summation. When touching them with the lips, the user perceives heat and pain due to thermal glue illusion. We conducted a preliminary test with 10 participants to verify the phenomenon, and all of them described that when touching them with the lips, they felt hot and pricking pain. We assumed that hot stimulation and the cold stimulation were perceived separately on the lips, so the participants felt hot and pain. Then we conducted an experiment with 2 participants to verify that multiple thermal stimulus can be perceived separately on the lips. 2 press devices were used for thermal stimulation. The task was to discriminate 4 patterns of thermal stimuli. They repeated it 20 times. As a result, 7 participants could discriminate the 4 patterns perfectly. The results mean that multiple different thermal stimuli can be perceived separately on the lips. We also conducted demonstration at a company exhibition and a domestic workshop. Many participants enjoyed it but some participants hesitated to touch the device with their lips. Now we are improving ThermalBitDisplay. This figure shows 2-bit version. One pressure device is used for providing neutral temperature by applying no current. The user can perceive thermal feedback by comparing the difference between the temperature. The other advantage is to enable robustness to outside temperature changes. For correct temperature control, a closed-loop circuit with PID control was implemented by using a microcontroller in the temperature sensor. The graph shows it works well. Finally, he proposed some applications. First, ThermalBitDisplay can realize haptic pre-notification, unlike vibration, which is used for haptic push notification. Thermal stimulation does not interfere with the user's attention by just wearing the device. When they want to get a notification, they can do it by touching the display with the lips. Second, ThermalBitDisplay consisting of 3-page devices can be used for haptic alerts. The pain does not occur by wearing the ring on the finger unless the user touches the lips with it. Therefore, it can prevent to put the fingers to the lips, and we consider it will be useful to prevent virus infection. Here is conclusion. ThermalBitDisplay provides different thermal feedback depending on the parts of the body touching them by utilizing 2 features of thermal sensitivity. In future work, we will investigate the feasibility and usability in the real world. We will design the gesture possible with the device more carefully in view of cross-cultural confrontations. That's all. Thank you for listening.
Thank you very much. So I can see a couple of questions already in the chat area. So like the first question is from Sebastian, that's he's asking about what spatial resolution did you use between each Peltier element? Arinobu.
Okay, thank you. The interval is 5 millimeter. Experiment 2. Yeah, only
okay.
Yeah, we conducted only one pattern, 5 millimeter.
All right. Yeah, next question is from Pedro. Does Pedro want to ask it, or shall I go ahead?
I can ask it if you don't mind, Roshan.
Yeah.
Me
Yeah, I
putting
think
my head in here again.
Yeah.
I don't know, that was really cool. I wonder, maybe I didn't understand it properly, but in the case that you called it a 2-bit display, so I had one Peltier here and one Peltier here. Did you feel that your participants could only feel the difference between the two? So I feel they're the same or they're different, in which case I really only have 1 bit again, because I can put that bit on 1, I feel a difference, or on 0, I don't feel any difference. Or could they tell this is hotter than the other, this is colder than the other, and in which case you then have all the 4 values again? Like, does it really do the 2-bit 4 values, or only difference? I didn't get that. Maybe you can elaborate a little bit.
In the experiments, the participants can answer 4 patterns. For example, the left side is hot or cold, and right side hot or cold. So it can they can answer off or on or off on or on.
Oh, so it's never at the same time. It's the pattern. That's what you're saying. It's this one and then that one.
Yeah.
Okay, got it. So it is a 2-bit display. I was wondering if they were feeling it at the same time. That would also have been an interesting thing.
Thank you.
Cool. Yeah, that was really interesting. And I also have a short question. Like, I noticed that you're not using any temperature sensors on the device itself. So how easy is it to repeat the exact like actuation patterns or the temperature change patterns?
In the experiment, we measured temperature before conducted experiment by using the temperature sensor, and we count 10 seconds to actuate, and then 10-second interval, and repeat the trial. And so we before experiment we measure it. The degrees is 25 to 27 degrees.
All right, cool. Yeah, thank you very much. So
Thank you.
I think, yeah, so we can move on to the next talk. So that's Mouillé, exploring wetness illusion on fingertips to enhance immersive experience in VR. So this is a live presentation by Mingming Fan. And yeah, thank you very much, Arinobu, for the talk and answering all the questions as well. So let's move on to Mingming for the next talk.
Thanks.
Mingming, yeah, okay.
Okay. All right. So thank you so much, Pedro and Jess, for your invitation. And thank you so much, Roshan, for chairing the session. Hi, everyone. My name is Mingming Fan. I'm assistant professor here at Rochester Institute of Technology. Today, I'm going to present you Mouillé. So this work has been done with my co-authors, Teng Han, Suri Wang, Sijia Wang, Xiangming Fan, Jie Liu, Feng Tian from Chinese Academy of Sciences and Carnegie Mellon. So wetness is a very familiar and important perceptions that we have about the moisture and the humidity of the surroundings. Here you can see like 3 examples of wetness sensations we're familiar with in our everyday life. Surprisingly, although this is a very familiar sensation, that the underlying mechanism has only been understood in the past 10 years by David Flingery and his colleagues. So David and his colleagues did a series of experiments to understand what make people feel the wetness. Basically, they used the true wet stimuli like wetted clothing with waters to understand the mechanism. So the key takeaway from their finding experiments was that we humans don't have the physical receptors for wetness. So the sensations of wetness is actually constructed by the feelings of the temperature change and the physical touch at the same time. So both of these 2 types of sensations we do have receptors for. So informed by these kind of physiological findings, then researchers in HCI domain are trying to generate the wetness illusions, especially for VR applications, to enrich their experiences. So Roshan actually is one of the pioneers in this area. He and his colleagues invented this device called liquid reality, which has thermal and vibrotactile modules so that it can produce the wetness illusions on the user's face. And they further extended the devices to include most sensors, other parts of the body. For example, they put sensors on the user's shoulders and their feet to generate the whole body wetness illusions. I think one of the cool applications they're demonstrating in their work is that the system allows users to feel a whole body illusion of wetness, like taking a shower. So informed by all these studies and the research, we also wanted to understand how we can leverage dry stimuli to generate wetness illusions on the user's fingertips. The reason why we're interested in fingertips is because the fingers have a lot of nerve systems in it, and also being used by us to interact with objects and with surrounding quite a lot in the VR domain. So we wanted to understand the underlying mechanism of the illusion itself, and it also wanted to design the prototype that can generate the illusion so that can help users to interact with VR objects. So the first step we took was to conduct the experiment to understand the 3 factors that could influence the wetness illusions. So these 3 factors are temperature, the pressure, and the friction. As you can see in this video, we actually modified a 3D printer so that we can precisely control the temperature, pressure, and friction. So see, here is the diagram of the system. There are different components, but here I just want to highlight 3 key components. So there is a FSR sensor, which can monitor the pressure of the system so that allow us to control precisely the pressure we wanted to apply to the user's fingertip. So there is a TEC plate, which can change temperature so that we can control the temperature on the user's fingertip. And then we also have this finger holder on the printer's platform so that we can precisely control the movement of the user's fingers to move the fingers to the platform to feel the temperature, and then to remove the finger from the surface to cool the finger down to the room's temperature again. I won't go into details of the study, but the key findings of the study are threefold. So the first is the higher the temperature change, the stronger the wetness illusion will be. So basically this confirms the previous findings with the true wetness stimuli. And we also noticed that the pressure and the friction can enhance users' wetness illusions if they're controlled in a proper range. So informed by the findings, and we designed a prototype called Mouillé. It has different components. So there are 2 key components to it. So one of them is we call stiffness control system, which has a locker system and a spring system that allows users to feel different stiffness of the prototype. And then we have the temperature control system, which allows us to generate different temperature change on that surface. So here you can see is how Mouillé operates in real reality. So basically here is how we simulate the cold Coke bottle. So as you can see in this prototype, Mouillé's locker system is in an unlock position and the spring is fully expanded. This allows the full expansion of the prototype to give user that flexibility of fitting. And then if the locker system placed in the lock position, and then we can simulate the hard object like ice cube. And then to simulate objects like wet spongy, we apply a layer of latex on top of the surface so that users can feel that sponginess of the surface. And to simulate the wet table surface, and we lock the system, and then we place the system in horizontally so that users can scratch the surface to feel that wetness illusion. And then we design a number of applications that allow users to feel these different types of wetness illusions. So basically, as you can see with the system, we'll be able to simulate the wetness illusion for ice cube, the Coke bottle, and the wet spongy, and also the wet table surfaces when the user scratch on that. And then we conducted a study. Basically, we wanted to understand with Mouillé, could users feel these different types of wetness illusions? So basically, could people distinguish, the wetness illusion of an ice cube from a Coke bottle and from a wetness spongy? And then the second question is, if users were able to feel these different types of illusion, could they feel different levels of wetness illusions? Meaning that if they can feel this really wet versus a little bit wet. Again, I think all the details in the paper here, I just want to highlight at the high level. Yes, our results show that users were able to distinguish the different types of wetness illusions. And for the different simulated wet object, users indeed were able to distinguish 3 different types of wetness levels for most of the objects. And for most of the objects, the accuracy was actually over 80%. But for the glass table, the accuracy was slightly lower, which I will go into that later on. So I just wanted to highlight some of the observations and the feedback from the studies, which we think are very interesting and inspirational. Here is that during the study, many participants actually asked us if we could help them dry their fingertip, because during the study, they were not allowed to see the system. So they didn't know what was going on to create that illusion of wetness. And they couldn't rub their fingers, so they wanted us to rub their fingers for them to dry the fingers. And then later on, when we asked them, what they think was going on, they told us that probably the system had a moisture generator, like a humidifier, and it might have a dryer which blow air to their finger to dry their fingers quick enough. And then maybe there is some mechanism to generate different types of stiffness. And here I wanted to point out 3 things we found interesting and sort of the limitation of the system, which we think that maybe the community can help address looking forward. So one of the things is that the wetness illusions that Mouillé generates disappears much faster than the true wetness illusions. By that I mean, when the user's finger lifts from the Mouillé system, and then the illusion disappears. That's very different from, you get your fingers wet by touching a wet Coke bottle, for example, because that true sensation will last for a while. And the second issue is that the weight of Mouillé itself is not always matching with the weight of the simulated objects. Take, for example, the spongy. Spongy is very light, but Mouillé is apparently much weight for that. So that, the moment when you lift the Mouillé, that kind of sensation was broken. Right? And the last one was that with our current design, we have very limited ability to generate different types of textures for the surface. I think if we can generate different types of surface fittings, we'll have a much richer sensations. I guess with that, I will basically conclude. We have 3 key points. One is we did an experiment to understand the mechanism of the 3 factors and how they influence the wetness illusion on fingertips. We built a prototype that can generate different types of illusion. We did an experiment to demonstrate that the Mouillé actually worked to help users to feel that different types of illusion. With that, I will conclude the talk, and I'd like to take any questions you have. Thank you.
Thank you very much, Mingming. That was fantastic. So, yeah, we do have a couple of questions coming in. So, yeah, first is again from Sebastian. So he asks, did you dry the hands of the participants before using the system? I guess, yeah.
Oh, yes. So for every single trial, we, first of all, before the experiment, we make sure their fingertip was at the not at room temperature, but at their normal temperature. Right? So, and then after each trial of the experiment, we will wait a while until their fingertips temperature, goes to the normal temperature that it used to be. So yes, there is no process to dry the fingertip because we don't use real water to generate the illusion. But we do wait until their fingertips returns to the normal temperature to continue the next trial.
Okay. Thank you. So Anton asks, did you measure the humidity of the participant's finger beforehand? And if so, did it affect the experiment? I guess in similar lines, if you did any pre-testing, yeah.
Yeah, that's an interesting point. That detail, as far as I remember, we didn't control the moisture of the fingertip. But maybe that my co-author could tell you more details about that. But that's, as long as my memory serves me, I don't remember we controlled the moisture, but we do control the temperature itself of the fingertip.
Yeah, yeah, I think it's also partly we are trying to give kind of a cold, dry stimuli, right? But it's just from the perception that you feel kind of the wetness on the fingertips itself. Yeah, that's really fantastic. And then Pedro asks, they felt the fingers were wet, and that's really fantastic, great illusion. I wonder, what do you think are the next steps on this? Is it trying to extend the duration? Yeah, you mentioned, maybe Pedro could jump in and clarify the question than me.
Yeah, sorry for making you read that. I was wondering, you mentioned something really interesting, meaning that that you were surprised that the illusion of this kind of wetness illusion was shorter than if I get my fingers wet right now on this bowl of water, right? And I'm wondering also if that's because the device, or we don't have a way yet to put the device rendering that evaporation stage, right? As the water sort of disappears, evaporates into the air, the temperature starts to change as the water content changes as well. I wonder, do you think that would be enough to make it more normal, or is that something else is missing, sort of physiologically?
I think what you just mentioned is probably one solutions we can tackle this problem. I think this is a very interesting problem we still don't have a good solution for, which is the illusion does disappear, you know, when the user remove their fingers from Mouillé, but that was very different from the real life experience. I think maybe one solution could be that we'll design a wearable system that could, you know, touch the user's fingertip, you know, for a longer time, so that they won't remove their fingers. So that maybe we can give them the gradual feelings, like a decay feeling of wetness. But that said, I think one thing we also notice is as the same thing, you know, we had for force feedback. You know, once user get stimulated with wetness illusion for long enough, they kind of become numb, you know, their fingers. So it becomes harder for them to feel the same level of wetness. The problem is some gaps. I guess what I'm trying to say is maybe there's some sort of wearable device design, and also we'll consider this persistence of the feelings. I think a combination of those two, maybe we'll come up with a better solution to generate like a more authentic like wetness illusion.
Great, thank you, Mingming. So Nimesha has a question about, did the participants feel numb in their fingertips after the repeated testing?
Not during the study though, because between the two trials, we did have a gap, so that, you know, we allowed them to their fingers to return to the room temperature. They had this gap to feel, to basically to return to normal state. So I think that's one of the challenges with VR application, we think, because in VR, if we wanted to provide this continuous feelings of wetness, I think that's still a challenge, because with Mouillé, you can only provide this temporal feeling of wetness on their fingertip. We're not going to be able to provide the continuous, let's say, a wetness for a minute or even longer than a minute, because you know, we didn't do the experiment, but we hypothesized that if you keep stimulate the fingertip with the same type of stimuli as we have for longer than, I don't know, maybe a minute, that people will become numb, as you just mentioned. Yes, they will become numb, that they will not be able to feel wetness anymore. So yes, that's a challenge I think as a community we can help to solve in the future.
Yeah, I think that's a great point. So yeah, I think we also felt the same way. So our demonstrations were always like maybe 5 to 10 seconds, right? Like beyond that, like people feel maybe, you know, not so, people feel numb towards the stimuli. So yeah. Okay, so we'll move on to the next talk. So we, thank you very much, Mingming.
Thank you.
So next is Therminator, understanding the interdependency of visual and, understanding the interdependency of visual and on-body thermal feedback in virtual reality. So it's presented by Sebastian Günther. Sebastian, please.
Hello, everyone. Yeah. My name is Sebastian Günther. I'm from the Technical University of Darmstadt in Germany, and today I present you our work where we investigate the interdependency of visual and on-body thermal feedback in virtual reality called Therminator. As we all know, virtual reality is becoming more realistic and has an ever-increasing presence for users. However, those new levels of immersion are nowadays still mostly attributed to an increasing quality of visual and auditory details. Further, recent works extend the immersion even more by adding haptic components such as vibrotactile feedback or similar mechanical forces applied to the user's body. While all of those features indeed leverage virtual reality to the next level, there are still other aspects which are not fully explored yet, such as thermal feedback. So you may ask, why do we need thermal feedback? Well, the most obvious reasons are of course to simulate warmth or coldness. However, we also need to consider such temperature changes on different scales, such as environmental effects or thermal object properties like a hot mug. And last but not least, temperature can evoke emotions in well or more beings through social experiences. Okay, so before we can apply thermal feedback to users, we need to have to look at some design considerations. First of all, we have to take care of the temperature range. Hereby, we need to consider the neutral skin temperature, which lies usually between 30 and 36 degrees Celsius. However, the range has to be limited since we do not want to cause any pain and take care of thermal pain thresholds, which lie at around 15 degrees Celsius as a lower boundary and around 45 to 52 degrees as an upper boundary. Besides the temperature, we also need to consider different anatomical properties of the human body, such as different shapes of different body parts. For example, we have a straight leg, a convex abdomen, or a bent spine. Further, as humans differ in size, body parts are also not equal. For example, the upper leg is almost twice the size as the lower arm and can even vary between individual persons. And last but not least, we do not want to restrict any movements and have to consider varying degrees of freedom of different body parts which can have multiple joints and are able to bend or stretch. So in summary, the requirements for thermal feedback are a good thermal conductivity, adapting to shapes and size, and needs to be flexible at body joints. As thermal feedback is of course not completely new, related approaches often rely on contact-based solutions, such as thermoelectric Peltier elements. Those have very good thermal properties and also have the advantage of being small, lightweight, and can provide very localized feedback. However, due to their nature, they tend to have a high power consumption and can restrict movements through their rigidity, especially when simulating larger areas. In contrast, there also exist non-contact based solutions which use external heating units or fans. Those also have good thermal properties, but also have the advantage to not hinder any movements. However, since they are not directly attached to the body, it is not trivial to actuate specific body parts while the user is on the move. So, to overcome those disadvantages, we thought, why not using liquids as a medium to transfer temperature? And for this, liquids have the good advantage to have good thermal properties and can be used very flexible. In particular, we had a look at water, which has a thermal conductivity of roughly 0.6 watt per meter times Kelvin. Of course, liquids need to be inside some container to be actually useful, so we decided to take tubes which we can adjust, bend, and where a liquid with different temperature can flow through. For this, our tubes had to have similar thermal conductivity as water and allows for enough flexibility, which we found in the tubes made of polyethylene of raised temperature resistance, or short PERT tubes. Using such tubes allows us to have different arrangements and numbers of interconnected subtubes in krill-like patterns to actuate small or large regions of the body. Further, we can reshape the tubes to adapt to different body parts and also are able to vary the length of each tube. As a proof of concept, we decided to design two actuators. The first can actuate the upper and lower arm. Here we use 8 subtubes which are connected through flexible PVC connectors to avoid movement restriction at the elbow joint. Second, we designed an abdomen actuator which aims to provide thermal feedback to a more flat part of the body and with a different anatomical shape than the arm. Finally, both are connected to our system's water cycle. So how does it look like? As you can see here, we have the PERT tubes in red, which are connected by very flexible transparent PVC tubes. In the current prototype, we'll use a flow rate of about 40 milliliters per second, which resulted in a temperature change of around 2 degrees per second, as visible in the thermal camera view on the left. For changing the temperature of each actuator, we mix a hot and cold water source using a thermal mixing valve. An electronic magnetic solenoid valve is used to control the actuation. We then measure the flow rate and inner temperature of the liquid and are able to adjust the flow rate through a pressure regulator. Then the liquid reaches 2 additional magnetic valves which controls the flow to the abdomen and arm actuators. And after having our system ready, we implemented 3 example applications which I will show you now. In the first, the user is a pirate on an island and needs to find precious gems. Those can be found in the water, which will cool down the user's arm when reaching for them. In the second application, a user plays a snowball game, and every time he gets hit by a snowball, the abdomen cools down quickly and slowly returns to the neutral temperature after some time. In a final application, we simulate an emergency task where the user has to put off fires in a building. The more flames are extinguished, the cooler the environment gets. And okay, after this we thought, why should we stop here? Because there's something we still can do, as virtual reality can simulate unfamiliar situations such as having hot burning ice cubes. So we ask ourselves, what happens if thermal and visual stimuli do not match the temperature expectations of the user? For example, on the left, snow turns warm, and on the right, the fire turns cold. Therefore, we defined 3 research questions which we wanted to investigate. First, how does the interdependency of thermal and visual stimuli affect the perceived temperature? Second, how do the thermal and visual stimuli affect the involvement of the users? And third, we ask how do the thermal and visual stimuli affect the comfort of the users? And to answer those questions, we first had to define how the thermal stimuli will look like. Hereby, we used the neutral skin temperature at 32.5 degrees Celsius as a starting point. We then increased the temperature in 5 degree steps until we reached 42.5 degrees Celsius, so we stay below the upper pain threshold. We also did the same in the opposite direction and decreased the temperature in 5 degree steps until reaching 22.5 degrees Celsius, which is just above the lower pain threshold, resulting in 5 total thermal stimuli. For the visual stimuli, however, we had to identify meaningful visualizations. As Fenko et al. Stated, objects convey different expectations of their temperature based on 2 factors. First, a literal or physical meaning, which conveys the actual temperature, and second, a figurative meaning that describes temperature by learned experiences. So to do so, we interviewed 7 HCI experts and asked them for visualizations, objects and other things connected to temperature, which they should rank from very cold to hot. Afterwards, we collected all the answers, clustered all items, and counted the column elements. This resulted in the following 5 visual stimuli, which we applied as visualizations for the arm as well for the abdomen. We have a very cold snow visualization, a cold rain cloud, no visualization as our neutral visual stimulus, a warm heating lamp, and a hot fire close to the user's body. For the procedure, I don't want to go into much detail. Basically what we did, we used a within-a-subject design with 25 participants. All of them were provided with a long sleeve, were sitting on a chair and wearing our actuators beforehand. Each participant either then started with the arm or abdomen, and during each condition we combined each thermal stimulus with each visual stimulus and exposed each combination to the user for about half a minute. Afterwards, we reset both to their neutral stimuli and asked to answer a questionnaire in VR, which I will show you in a second. In total, this was repeated for all 50 combinations. At the end, we asked for additional qualitative feedback through a final questionnaire and informal interviews. As mentioned before, after each combination of the visuals of the stimuli, we asked to fill out a questionnaire with the following 4 questions. How do you rate the thermal sensation? How do you rate the thermal comfort? How much did the visual aspects involve you? And how much did the thermal aspects involve you? In the following, I will present you our main findings. However, if you're interested in more details, especially in lots of numbers and statistics, I would like to invite you to have a look at our paper. So, okay, let's dig in to our results. As the first main result, we identified that every thermal stimulus always overrides the perception of visual stimuli. So for example, if we have a fire visualization combined with a cold stimulus, it still feels cold. As you can see here, where a lower number basically means a lower perceived thermal sensation and a higher number means a higher perceived temperature sensation. This was true for all other visualizations, and the participants were always rating the applied thermal stimulus as main factor for their temperature perception. However, if we take a closer look to the numbers, we can see that the visual stimuli still have marginal effects on the temperature perception. For example, for a neutral thermal stimulus, we see a significant higher rating while being exposed to a fire visualization compared to a snow visualization, which is also indicated by differences in the minimum and maximum ratings of the participants. One interesting side effect we could observe was an unexpected small shift for the rain visualization, which resulted by some participants describing it as warm shower instead of a cold rain cloud. Regarding the involvement, we could identify that congruent stimuli increased the involvement. As you can see here, a neutral visual stimulus, so no visualization at all, resulted in no involvement as expected. However, similar as before, a neutral thermal stimulus is affected by the shown visualizations, as you can see here. Taking a closer look at matching stimuli, which we can find at the lower left and upper right parts of each graph, we can clearly see significant higher involvement ratings as compared to non-matching stimuli, which were often described as uncanny or even uncomfortable. Last but not least, with regards to the participants' comfort, we found that the level of comfort highly depends on the applied thermal stimulus. As you can see here, our analysis revealed a significant higher comfort for neutral and slightly warmer temperatures compared to colder stimuli. As a result, the overall consensus was that temperatures generally could even be warmer, but should not get colder, as more chill temperatures were perceived as uncomfortable and more intense. And before concluding my talk, we, of course, identified some limitations. First of all, we only investigated the abdomen and arm and need to identify how other body parts will perceive the thermal stimuli provided by our system. Also, we only combined one visual and one thermal stimulus per condition. However, what would happen if we have multiple stimuli combined at once, or even actuate different body parts with different stimuli at the same time? And lastly, while not described as restricting the users more than the HMD cable, our system currently relies on an external source which needs to pump the liquids to the actuators. Hence, we need to find reliable ways to increase the variability, for example by having smaller amounts of liquids and thermal devices in a wearable backpack. And hereby I want to conclude my talk where I presented you Therminator. I presented you a set of concepts and design considerations, a prototype along with 3 example applications, and a systematic evaluation investigating the interdependency of thermal and visual stimuli, where we found that thermal stimuli always override visual stimuli, congruent stimuli increase the involvement, and the comfort depends on the thermal stimulus. I would like to thank you for your attention, and if you have any further questions or comments, feel free to contact me directly. And also, if you're interested, check out the other great Chi 20 talks by my Team Dasha colleagues from the Tele Cooperation Lab. So thanks and stay healthy.
Thank you very much, Sebastian. So yeah, let's directly move on to the questions. Yeah, there's a question from Abdullah. So he mentions it's interesting, did the participants report tricks like closing their eyes during incongruent conditions, or any other strategies for dealing with such incongruence?
Well, thank you, Abdullah, for the discussion. Actually, the short answer is no. As far as I remember, there was no like closing the eyes or something like that. However, if it was uncomfortable or like uncanny when the stimuli were incongruent, people were just starting to complain and hoping that it ends.
Thank you. Yeah, next is from Jess. Was a flow detectable by the participants, like for instance, the vibration from the tubing, or was the pressure regulator used to avoid this kind of unintended feedback?
Thanks for the question, Jess. Well, actually, yes, you could feel some vibration of the tubing. However, we made sure that the tubes are very tight attached to the body. And yes, also the pressure regulator, which regulates the flow to 40 milliliters per second, was limiting the vibration a little bit. However, yes, the whole system had vibrations, but as far as we know, it didn't have any effects on the thermal perception.
Okay, thank you. Katie asks, have you considered any applications outside of VR?
Thanks for the question, Katie. Basically, yes. Well, our focus was, of course, virtual reality. But for example, you could imagine also some error prevention system, which was also described by Arinobu earlier today. So for example, you should not touch something and your body gets hot before you even touch some hot valves, for example.
Thank you. Yeah, I'm also curious about like how you control the temperature. Like for instance, did you have any temperature sensors on the skin level to kind of monitor how fast the temperature changes at that level?
Yeah, thanks for the question. So we had one temperature sensor inside our system. So we directly measured like the temperature of the systems. So while we only had like a mechanical mixing valve, we still saw immediate changes in the temperature and could adjust and counterbalance it. Also, we took care that we have some like adaptation time until we have our target temperature, for example. So we waited for some seconds until we actually started like the visual stimulus. On the skin level, we didn't have an additional temperature sensor. However, we measured it before in some more informal tests to see how good the temperature changes. So in general, it was about 2 to 5 seconds until the skin had like the same temperature as the inner temperature.
Understood.
Liquids.
Thank you very much, Sebastian. That was really cool. So literally.
Thanks.
Yeah, so we'll move on to the next talk. So the next talk is on ThermalWear, exploring wearable on-chest thermal displays to augment voice messages with effect. It's presented by Abdullah El Ali. Yeah, Abdullah.
Hello everyone, my name is Abdullah and I'm a tenure-track researcher at CWI in Amsterdam. This is a teaser video of our CHI 2020 work titled ThermalWear, exploring wearable on-chest thermal displays to augment voice messages with affect. This is a joint collaboration with my co-authors at TU Delft and the University of Oldenburg. So why study voice emotional prosody? Well, emotional prosody can be situationally impaired, an example ironic speech, or remote communication settings such as avatars or occluded gestures in Zoom meetings. It can also be impaired in certain medical conditions such as autism spectrum disorder. And finally, for intelligent voice assistance, emotional prosody may still not be human-like and requires amplification, for example, to indicate urgency. So there's been quite some work investigating the relationship between emotions, media, and temperature. And what's important to note here is that the common finding is that warm temperatures are generally associated with being pleasant, comfortable, and increasing social proximity, while cold temperatures are not. So in this work, we draw on the bodily map of emotion by Nimesha et al. And overlay 3 of Ziegler's wearability body maps. And we find that the upper chest is a suitable thermal stimulation site. In this work, we contribute ThermalWear, which is a wearable prototype that thermally stimulates the upper chest, and empirical findings that show that neutral voice messages can be effectively augmented with affect. All our source codes available, so please take a look. This is what our perhaps clunky prototype looks like. But please look at the paper for details on its construction, the real-time temperature readings from the Peltier elements, the thermal perception findings, and comfort of such simulation. Let's go over some of the findings of our first experiment, which was meant to firstly validate that our thermal display can be indeed used for voice message augmentation. So here, we ran Friedman rank sum tests and post-hoc Mann-Whitney tests with Bonferroni correction to assess pairwise differences where applicable. 2 observations can be made here. First is a sanity check that warm temperatures are indeed warm and cool temperatures are indeed cool. Second, as in prior work, our results overall support a consistent finding that perception of cold thermal stimuli, whether it's due to participant sensitivity or detection times, is generally greater than warm stimuli. With respect to user comfort ratings across warm and cool stimuli in differing intensities, here we found no significant effects. For detection times, two observations can be made here. First, detection times without fabric are faster, and second, higher intensities are faster. So for warm stimuli without fabric, the average detection times range from 8 seconds for low intensity to 4.7 seconds high intensity. For cool stimuli, the average detection times range from 5.5 seconds low intensity to 5 seconds high intensity. So due to this, we chose to continue testing for experiment 2 without any fabric. In the core study that we've done in this paper, we draw on the EU Emotion Voice database, where we selected 8 messages and synthesized neutral counterparts using WaveNet. We ensured that these were indeed perceived to be neutral through an annotation study that showed high intra-class correlations. So first I'll play the EU Emotion Voice version, and then followed by the version that we generated.
I love chocolate.
And now the neutral version.
I love chocolate.
And for our negative valence message,
cover your mouth when you sneeze. Cover your mouth when you sneeze.
there's a lot more details in the paper, which aids in reproducing our work, so please take a look if you're interested. For this study, we had a 2 positive versus negative message valence by 3 warm versus cool versus no stimulation design. After experiencing the stimuli and voice message simultaneously, participants entered their valence and arousal ratings through a 9-point self-assessment mannequin scale on an Android app. Since our data was not normally distributed, we applied Friedman rank sum tests and post-Huckman-Whitney tests with Bonferroni correction for pairwise comparisons where applicable. But what do these results mean? First, thermal stimulation influences valence of a neutrally spoken voice message, but this, however, varies across cool and warm stimuli. Second, while warm stimuli increase the valence of positive messages, this is not so for negative ones. Cool stimuli, on the other hand, lower the valence of both positive and negative messages. While our results support Salminen et al.'s classic study that showed that warm and cool stimuli can increase arousal over neutral, our findings, however, differ from Tewell et al.'s work on thermally stimulating Facebook posts, where they don't find an effect of thermal stimulation on valence ratings. And so finally, based on our semi-structured interviews, we see similar patterns as before. So for warm stimuli, most participants found that positive messages became more positive. So like P3 said, if it's warm, I can sense the positive emotion is sincere. For cool stimuli, most participants found that such stimuli lowered valence of positive messages. So some examples include like P1 saying, I feel it's not that positive anymore, or P8 finding that it lowers sincerity, or P2 saying that cool stimuli makes it more angry or more severe. So there's a number of considerations from our work which I'd like to go through. So first, it appears that warm and cool stimuli are comfortably tolerable on the upper chest area, are easily perceived and quickly detected. Also, we need to consider the trade-off between user comfort and detection time when adding fabric. In our case, adding fabric did not provide more comfort, and was at the cost of detection time. Third, as shown also in prior work, the message context matters whether thermal stimuli influence both valence and arousal or only arousal. In our case, we had brief voice messages, which were standalone units of conversation, and so thermal augmentation works well here. Also, while we tested this and discussed it in the paper, we did not, and perhaps cannot, recreate missing emotional prosody in a consistent manner using thermal stimuli. So in this case, this goal is probably not one to pursue. Finally, we can wrap up with a number of key design factors that we found can aid in constructing such thermal augmentation displays. So first, which fabric and wearability comfort are we aiming for? Second, what for the designer and the target user is a suitable temperature perception and comfort, and what detection time is required for such a design? And finally, what is more important, thermally stimulating valence, arousal, or both? And on which body location? So thank you very much, and please refer to the paper or the longer CHI 2020 paper video for details. And please feel free to drop me an email or send me a message on Twitter for any further questions. Thank you again.
Thank you very much, Abdullah. So is there any questions from the audience? If not, I have a couple of questions. Yeah, so in terms of the location that you chose, could you explain a bit more about like what other locations might be suitable for this kind of emotion-related thermal feedback? And yeah.
Thank you very much. It's a good question, and this is the one question that's been bothering us all along, is because we didn't find any work that somehow tries to relate what's a good body site for stimulating emotions. So then we dug into the literature and we found the bodily map of emotions by Newman et al. And even though these are based on self-reports but they had thousands of participants, and it seems that the chest is a common area for feeling different or experiencing different emotions. Of course, there's many other problems with the upper chest area, which we've come to discover. But so this was a starting point, and we thought, let's go, since our goal is really to stimulate emotions, then let's just follow prior work and see how far it takes us. But whether it's a practical solution in the long term, then I think this is not the right approach, which we discuss and reflect on in our work.
Yeah. I personally like that approach because I think, you can design future wearables like, necklaces and things that have recently we've seen things like smell devices and things like that. So we can integrate a lot of other things with your research as well. So I think there's another question that's asking about what are your thoughts on using vibrotactile feedback in combination with ThermalWear for, I guess, emotions. Yeah.
Quite frankly, I don't know, because it might provide too many confounds between providing haptic feedback plus thermal feedback, and there's a thin line between augmenting a voice message to increase or lower its valence and arousal to just straight out increase arousal. Mm-hmm. Because if we're feeling too much from different modalities, it might also defeat the purpose. And so this was an initial exploration of to what extent. So we were thinking of voice assistants, and in the end, we're thinking of embedding material elements in, let's say, cushions or couches. So then, if you were to receive a voice message, would you be able to know what the valence and arousal is of the person sending it? So this is our logical next step. But at first, we want to see, is there even a relationship between coolness and hotness and what somebody's voice sounds like?
Great. Thanks. And yeah, Yosh has a recommendation. He mentions, don't know if it's helpful, but molecules of emotions, cadence spurt might be interesting. Yeah, I guess you can take a look at that.
Thank you.
And
Jazz, I did not know about it.
Yeah, there's a lot of questions coming in now. So Jazz asks, how would you imagine creating future versions of ThermalWear that could produce more complex emotional augmentations, whether that's temporal or future combinations of locations you'd be interested in?
Yes, so I also think what Sebastian mentioned earlier and said the limitations of context-based solutions is that they're extremely power hungry, these material elements. So the fact that we're thinking of a wearable that we could just receive voice messages on the phone, at least in today's landscape, doesn't seem very practical. Mm-hmm. So what we're thinking then is, as I mentioned earlier, to just embed this in furniture. So if I'm already sitting down and I'm getting a message on my phone now, then this may be a good way to augment, let's say, an interaction, or if I'm talking to Alexa, let's say, to give a bit more of an immersive experience. Mm-hmm. Yeah. But the whole wearability aspect and having a pulsar element, I mean, participants had to literally sometimes hold the system to their chest because it was heavy and bulky.
Yeah, actually, I noticed that in one of the pictures, I can see the participant holding. I wrote it down as a question as well. Yeah, I think
it's deliberate a lot to show this,
Yeah, that is a good point. And yeah, so there's a lot of questions coming in. So I think we can probably move into the panel discussion, and I'll go through the questions for Abdullah, and then we'll go through the questions for everyone through the panel discussion. Does that sound good to everyone? Okay. Yeah. So firstly, I'll just ask the last question from Yosh. Is it suitable to detect a wide range of emotions because some people don't have high EQ or perception of situation awareness that might not be as advanced, so their body might be reacting to something not the intended emotion?
Yeah, so I think earlier there was a talk by Dimitris on scents and how they could be used to induce pleasantness or anger, etc. And of course, the question is there some universal agreed upon ground truth by which an emotional elicitation method could be used? And in this case, it very much varies. Some people are very much in tune with their body. I mean, we had one participant who just could not finish the study because he felt too sensitive when it came to experiencing this. So let alone emotions, the whole sensitivity was already a reason enough to quit the study. So in this respect, yeah, it could also give the unintended emotion. But what we found interesting is that if it was warm stimulation for a positive message, it made the message much more positive. But if it was cool stimulation, then it felt very sarcastic or insincere, or as if the person's like, yeah, this is exactly what it is. And I thought that's interesting because we could be experiencing these effects anyway. Like if you're talking to somebody when it's really rainy and cold, or if it's a nice sunny day, maybe it could be the same message content, but just interpreted radically differently. And this is the kind of work we're trying to, coming more from the emotion research perspective, and to what extent it could be modulated.
Yeah. Cool. So yeah, I think we can move on to, there's some comments about the multisensory overload from Alex and Jess. So I think there's a lot of interesting things coming up through this discussion. And I think one of the fascinating things about this particular session was that I saw a lot of different types of uses for thermal feedback, like not just like, evaluating how thermal feels like on the skin, but, coming up with illusions like wetness, or, looking at multi-bit displays that are kind of like on-demand displays, for instance, and even like, generating or like looking into more flexible type of actuators for thermal displays as well. And yeah, I think that's kind of a fascinating way to look at this session. And yeah, so I'm curious to ask all the authors in the session, like, what are your thoughts about like where the future of thermal feedback is going? I think this is something that everyone's thinking about, like in terms of, we see a lot of research focusing on virtual reality and like emotions and other kinds of applications of thermal feedback. So what are your thoughts on the future of thermal feedback and how it will come into the consumer market? So I'll start with Mingming first because he's appearing first in my list. So yeah.
Okay, so
yeah, sorry.
thank you.
Yeah.
That's really interesting question. So I personally, I don't have much experience with doing a lot of VR and thermal related research. So Mouillé is just one of the first kind of research where we're trying to look into this space. But from the lessons we learned from building Mouillé and exploring this sensation is that one thing we learned is that people's ability to feel this type of sensations are different. So I didn't mention in my study is that we actually encountered participants who couldn't feel the change in temperature that much. So therefore, they couldn't feel the wetness illusions, which is derived from the temperature change. So I think maybe in the future, one of the challenges will be how can we provide this type of simulated sensations, customize the simulated sensations for to different people with different abilities. I think that's one. The other one, as Pedro just also commented on, is how can we make this set of illusions last for a longer period of time, so that when they interact in the VR environment, it's not just a momentary experience. It could be a on-demand type of illusion to them. So I think that's two on top of my head that I can think of.
Okay. Yeah, thank you very much, Mingming. So we'll move on to Sebastian. What are your views on this?
Yeah, I think Mingming is right. So I agree on this. Additionally, I would say one of the biggest challenges with thermal feedback is like the usability and variability of such actuators. I mean, we saw a lot of different things today from Peltier elements, which again, either small or very power consuming. Or like, for example, our system, Therminator, where we need a lot of liquids at the moment. So either if you want to cool down or heat up different things, we need a certain amount of surface to do this, or a lot of energy. And both is still very tricky because we don't have very small actuators, especially if we compare to other haptic components, for example, projectile feedback. We have small actuators, they can work pretty easily, or also a lot of work done by Pedro with the EMS actuation. This is possible to reduce in size, however, with the thermal actuation is still a bit of a challenge. However, I thought it was a really nice presentation in the US morning. It's already late evening from Jazz, who did a completely different approach with like this scent of different liquids to change the overall temperature sensation.
Yeah, I think that was a fascinating work. So if anyone's interested, please check out the trigeminal temperature illusions. I can't remember the exact title, but something like that, in the previous session on smell, that's also looking at giving thermal feedback through smell sensations. And Arinobu, what are your views on bringing thermal into like the future?
Yeah, now I'm interested in online haptic communication. In the it is important to communicate not only information but also transmit emotion or feeling. And today's presentation, many presentations show that thermal stimulation can present comfortable or uncomfortable or even present pain. So I think thermal stimulation is the transmit emotion is a very strong point compared to other tactile stimulation like vibration or electrical stimulation or ultrasound stimulation or air stimulation. So this year I want to challenge to communicate emotion or feeling with the thermal stimulation, thermal feedback. And the advantage is the system is very simple. It can provide thermal stimulation, the small Peltier device. So I think online haptic communication is one important application.
Thank you. And Abdullah, what are your views on this?
Well, to be quite frank, I'm not really a thermal researcher per se. So I'm coming from emotion or affective computing, and we're trying to develop all kinds of techniques to ensure that our devices can be emotionally responsive and can create a bit more harmony with humans. And so thermal feedback is just one means to sort of enhance this kind of aspect. But judging from the talks earlier to do with smell and thermal and then later taste, well, the kind of nightmare future that I would imagine is that we have all these devices happening and I'm suddenly overstimulated in every aspect. And I think researchers would probably need to start kind of defining some kind of either adaptive rules for when to stimulate what when, on which body part. And of course, everything works very well in a lab setting, and then yes, we can distinguish between these two. But what would happen if I'm smelling a scent, having thermostimulation on my lips, also on my forearms, a wetness illusion here, and this is kind of a future which I don't necessarily like want, and maybe this is something that could be seen as a challenge for any kind of multimodal interaction, but also a lot of the work that tries to stimulate the senses. I mean, the senses are already quite sensitive to many aspects. Some people are hypersensitive, some people aren't. So using specific domains, maybe it's important, but I find the combination interesting, of course, with the grand goal of going towards to have better emotional communication and recognition.
Thank you. Yeah, I think that's a really good point. And yeah, I can see a lot of conversations going on in the chat about agency and there's some. Pedro, do you want to jump in on anything?
Oh, I was just fascinated by some of the points that Abdallah mentioned, and I think he just mentioned them again. Of there's a lot that we don't know, and especially I think these lab studies that we do, we always try to generalize as much as possible. But then there is a confound, which is that once a device is put onto someone, we can't generalize anymore because it's for that person. So hypersensitivity and personal variations and all that becomes then super important. And I love your comments, Abdallah, on that. I think that's a big challenge, maybe that thermal and olfaction and a bunch of other fields have to go through before we can even roll them out to other people outside. I don't know. I like those thoughts.
Yeah, I think that's a good point because most of the time, in my personal experience also, like most of the research was always kind of motivated by the feedback from the participants. And like we just do some kind of a basic thermal study, and then they say, oh, I remember, like it was opening an oven, or, did you spray water on my face? Like these are actual feedbacks that kind of led into different directions of our research. And yeah, I'm just curious to know what kind of motivations led to your research, like especially because there's so many diverse set of applications that you're looking at. So yeah, if you can jump in on that, maybe starting with Mingming.
Okay. So one of the things I'm personally interested in is about like different types of sensations we can provide to this VR environment, which is mainly visual dominant, right? So I think thermal feedback, wetness illusion that we're looking into are just examples. There are also other ones, olfactory ones, smell, taste. I think all of this, we can bring these sensations together into VR that we can create more realistic or more rich feelings for the users. I think in that direction, I think I'm quite excited about that direction. And I think what some of the challenges, again, as many of you guys mentioned about personalization, how do we design customized systems that can cater to a particular person's sensation abilities, for example? How do we make the devices small enough? Like even in Mouillé, our system, that we mentioned the weight of the system it doesn't match with some of the virtual objects. How can we also match other aspects of our prototype with the objects we try to simulate, so that they not only provide the sensation we want, but also other types of properties also match with the physical objects. I think toward that goal, I think it requires a lot of expertise from I think different aspects to make this happen.
Thanks, Sebastian.
Okay, no. Yes, again, I agree what Mingming said. And also, I think a lot of the issues we have with thermal feedback are not limited by thermal feedback. For example, I go a lot into the direction of like the whole somatosensory system, which also covers like proprioception and so on, and also pressure feedback, and it's all like haptic feedback system, which often needs some, besides a lot of energy, also some force that need to be applied to the body in what moment to do.
Thank you, Sebastian. Arinobu, anything you want to add?
Yeah, I think the energy consumption is one big problem for thermal stimulation. In fact, our system continue for 1 hour, 2 hours. So we have to some other actuators to use in daily life and continuous use. And other thing is the perception is different from individuals. So I also agree with personalization for thermal feedback.
Thank you, Abdullah, anything?
This last comment's quite interesting. I mean, yeah, imagine we were all having, let's say, thermal bracelets, let's say. Does this change our day-to-day perceptions of how sensitive our skin is for the site that's stimulated? And then do you bring these people to the lab to test them? Do you have to calibrate the system beforehand so that we could see effects and find differences? And yeah, I think it's clear that at some point we do strive for universals and to generalize, but the true story is that the reason in HCI we include subjective reports on top of the quantitative findings is because there's going to be variability, variance, disorder, whatever you want to call it. But it's never going to be a clear-cut picture. We can talk about averages, but some of those things aren't necessarily just averages. And that's, I think, a key point, which I think everyone who's tried to kind of modulate or tune a human being or amplify them in one way or another will have to realize at some point, is that there isn't a one fix for everything.
Yeah, absolutely. I think when it comes to these kinds of personal sensations, like I was also like quite interested because, you know, when you try to report it, like self-report it, you know, there's so much variability that you might encounter, and it's very difficult to overcome that. And right now, I believe like the physiological sensing is not strong enough for us to have a reliable measurement for these kinds of purposes. So yeah, it's like with sensations like thermal, smell, and maybe even taste, like, you know, it's very difficult to quantify what a person feels so that we can have kind of a unified system. And yeah, I think as Pedro also mentions, how to design for variability is kind of a big question that we all need to think about. Yeah, so
quick comment on that.
Yeah, sorry.
I mean, also with the generalizability, so that's correct English word, I don't know. Generalization. Of like thermal sensation and so on. It's not easy. I mean, even when we planned our system, it's hard to find like this one solution or one answer to, for example, where's the neutral skin temperature? It always is a range between, I don't know, 4 or 5 degrees, and even we try to center our neutral stimulus at like the neutral average skin temperature level. But as we could see in our results that, for example, warm temperatures could even be warmer, even if the pain thresholds were very close, especially compared if our lower limit, which was like, I don't know, 5 to almost 10 degrees from the cold paint threshold, and people already started to say, oh, it's way too cold, feels uncomfortable, and so on.
Absolutely. I think that's a good point about the safety of the stimuli that we can produce with these systems as well. So yeah, I think I myself have burned so much when designing these systems. And I'm sure Pedro also may have, like, you know, had all these muscle stimulations, you know, going crazy. And yeah, sorry, go ahead.
Yeah, I mean, we also tried, like, I mean, I tried on myself, how far can we go? I mean, the lowest limit for the coldness was 17 degrees we could reach in our system. However, we could go up to, I don't know, almost cooking water. So I think the maximum I had on my body was around 60, 65 degrees even for a very short time. And then it really started to hurt. For example, if I go from the literature and have like only this 50 degrees as a pain threshold, for myself, it was still like not too bad.
Cool. So it looks like maybe Alex might have a question. Let me see if I can unmute him.
Go ahead, Alex.
Hey, if you guys can hear me.
Oh, yeah.
I guess, one of the big things, the themes that I really like about this design for variability point, Judith brought it up earlier in her presentation when she was looking at sort of the social acceptance of her wearables. And honestly, this is one of the main attractants that I had to come to see this Kai presentation, because it's often, I mean, all this stuff is amazing research, but when it comes to commercializing it, or even just, you know, releasing it to patients or for therapeutics, that can be one of the biggest breakers for its success, more so than whether it's even accurate, is the perception of it. So I just really appreciate this conversation, and I just wanted to comment on that.
Yeah, thank you very much. Anyone wants to comment on that? Okay. Yeah.
Well, I can just say, also here, I think it always applies a bit with the use case. As I said, if you have like some therapy use case, you don't want to have like a very bulky system, or if you have to want something which is more focusing on mobility or outside or ever prevention in whatever scenario, then of course it needs to be small. However, then you maybe do not need like a full body activation or something. So like smaller system, like a bracelet or so, would already work for the certain use case.
Okay, so I think we are reaching the time limit for our panel discussion. So I would like to thank all the authors and everyone who participated, asking questions and everything. So thank you very much, everyone, for the cool session. Right. So yeah, I guess next will be the test session, and I'll maybe pass it on to Pedro and Jess to take over.
Thank you for this event, and thanks, Roshan, for
Thank you very much.
Thank you very much, Matthias.
Thank you, Roshan. That was really amazing. So everyone, we just finished the second session, right? So that's the one that I highlighted on my screen. This was the session on temperature. If you didn't catch the first one on smell, which we all made a few reference to it on our discussion, once the event is done, you'll be able to see it on the YouTube link that we also distributed on the event page. Next up would be our session on taste. So we're having a larger break now. So it's, I believe, 3 p.m. now in Chicago, exactly 3 p.m. And we're having a 3.5 hour break just to give some time for our co-authors in Asia who are presenting some of these papers to also have a better time zone for them. So please join us if this is harmonious with your time zone in 3.5 hours for the taste session. And feel free to bring whatever foods you're eating at that time, and just let's eat it on Zoom. That sounds like a really great idea. And once more, thanks Roshan and everyone for this awesome temperature session. See you in a little bit.